I hope everybody's doing okay. Today, I want to talk about this little doodad here, which is a strain wave gear reduction. This particular model is of a 31 to 1 reducer that I found on Hackaday. So if you go to hackaday.io and you search for strain wave, this strain wave by Leo Vu is the one that I chose. Now there's a whole bunch of strain waves on here, and they all have varying issues. The one that actually got me excited about this project was the one by Simon Merritt, who's inspired me for a couple projects now. So hopefully, if Simon Merritt sees this, thanks so much for the inspiration. This one's really interesting because it uses a timing belt as the tooth form for the flex spline. They're kind of hard to make, and because timing belts are pretty strong, it was a really good idea of his to see if he could get that to work. He gave up on this prototype, but I think it actually got quite a few people trying to make one. Bart Dring made one with flexible filament that was pretty interesting, and this one seems really good. There's a bunch of videos on YouTube, but in the project here, he's actually got the step files for 3 different reductions. And what makes that great is I can import it into Fusion 360 and play around with. If I go ahead and add a section analysis here. Anyway, so here is the actual cross section of the design. And I've actually read a whole bunch of patents about strain waves devices and you know, a bunch of different things that are kind of related to this. And the patents are very hard to read because you'll you'll get like a very you know, you get a cross section like this with a bunch of numbering, but you can't actually look at it in 3 dimensions. So this having this model is actually pretty handy. So anyway, if we start to remove a few things, this is the motor, and this other piece that I've hidden is a bearing. Now he chose a pretty expensive type of bearing called a slewing bearing, which has it has some attributes which are really nice for this application. The main one is it can handle very high loads, and so the fact that he designed this all around a big slewing bearing means that the output flange should be able to handle considerable loads, and it's pretty compact from top to bottom. The downside of that is the slewing bearing that he picked is about 150 bucks just all by itself, and I don't have one on hand. I do have a bearing that's got a 90 millimeter outer diameter, and it has a 70 millimeter inner diameter. This one, I believe the inner diameter is 90. So yeah, it's 90 plus a little bit of room, I guess, he built into the model. So this is a much bigger outer diameter than anything that I have. So I need to shrink this down. But anyway, let me just very quickly run through the components. So the first component that I want to remove, rid of that. Before I get rid of it, I'll just talk about it real quickly. This plate, it may not be immediately obvious if you open the file, but this plate is designed to hold small 10 millimeter roller bearings, and those roller bearings, if I get rid of the section analysis here, those roller bearings, you can see that they are kind of gradually pushed out closer to the edge. So at these 2 points, they're actually pushed out where this recess for his nut is interfering with his with the radius on the part here. And this is okay. This will create an elliptical shape that will push the inner spline to engage the teeth here. The problem with this is that there's quite a bit of hardware that's going to be sticking out all over the place, and I think the bearings that he picked, they're only 4 millimeters high. So you only have a 4 millimeter contact area that's doing your pushing. So you can see right here, that these two teeth, if you were to push this round piece, if you were to push on that, those teeth would engage at this one point. But if you look over here 90 degrees, not only do they not engage, but they're actually overlapping. And so the sizing of this inner ring, which is called the flex spline, is bigger than can physically fit in here without deforming. And that's by intention. That's the way the strain wave actually works. So the ellipse that you create with the wave generator is the thing that's going to push this tooth to engage, and as that moves around the circumference, it will engage subsequent teeth, and the wedging and rolling action of that engagement is what will drive, that actually creates the differential movement to create the gear reduction. I don't know if I explained that very well, but again, the way he's creating this wave of flexing in the flex spline is through this bearing contact right here. So it's this whatever 10 millimeter bearing. If you look at the more if you look at the harmonic drives, or you look at some other people who actually professionally make these strain waves, you'll see that in some cases they have a special bearing that's actually an elliptical bearing, and that bearing, it's a very small ellipse, and that bearing is what is actually going to be driving the flexing wave in the flex spline. So if you look at this video, you can see that he's squeezing it, and as he squeezes the outer race, let's play that again. As he squeezes that outer race, the inner race is actually rotating, and the reason that is rotating is it's trying to find a position where there's the least amount of strain on it, and because this is longer than this, that inner race will go ahead and move on his squeezing. I'm not explaining that very well, but if you look at it, maybe it sinks in your head like it did for me. So because you're spreading your load out across these ball bearings instead of actual 10 millimeter encased smaller bearings, I think you get less friction in the device potentially. The other problem that I see is, if we go back over here and we look at the ellipse driver, now if you were to imagine a shaft running here holding a bearing, all the forces are going to be pushing back this way, which is going to bend, it's going to create a cup shape across this entire thing. And if you look at this design, all the forces they're all radial. There's no axial forces here, meaning any pressure at any point along this isn't going to cause the central hub to deform into a cup shape. And so I think not only mechanically is this, it's not optimal, because you not only do you have all these nuts and bolts, but on the other side in here, you're going to have to attach the flex spline, and the mounting hole you can see right here is going to require a bolt head, and the other side of this elliptical driver is going to require a bolt head. So you've got a bolt running down through here, and you got a bolt running up through here, and that limits it. Not only does it limit the amount of working space you have inside of this, and the amount of contact area that you can mesh the two sides of the flex spline, but again, you get this potential for a cupping action, and under load this whole plate deforming, which I don't think is optimal. So that's a pretty long-winded explanation, but that is I think that's the problem that I'm tackling here in my description of how to actually make one of these elliptical um, bearings. Now, this one, I'm not sure how they made it, but I have a couple ideas on how you could fabricate one out of aluminum or some harder material. They're very involved. They would require a bunch of different setups on different machines, and you know, it's a lot of work just to do some prototyping and testing. And so I thought maybe there's a way that I could print I could print a elliptical strain wave generator for this device. So anyway, the way that the flex drive works in this, the way a strain wave generator works, is that one of the inner ring or the outer ring needs to be fixed to something that will not move, and the stronger that is fixed, that directly impacts the overall rigidity of the entire device. In this design, the inner ring is fixed, and the outer ring is the drive ring, and this upper, what's called, I guess in this drawing, the lower circle, this is the actual output drive ring that you would use to drive whatever the output is that you wanted to drive. So back over here, I have the flex spline and I have the outer ring gear, and I've scaled these down. And because I didn't know exactly what the right scale factor was, I did a little bit of trial and error, and I used a body that had a 70 millimeter outer diameter. And you can see I didn't quite get it lined up perfectly. You can kind of see the model through the other model, and it's a little, these lines are a little fatter over here than they are over here, but it's probably a very nominal amount. And I think the ratio I scaled it at was like 70. It's 77.3, and that's what got me this final dimension on this, the outside of this, to get that to whatever it is, 70 millimeters. I scaled it uniformly. I actually probably should have just scaled it in the X and the Y, because I don't need any Z scaling. But that's a whole nother story. Anyway, back to the whole elliptical bearing design. So the first thing I did is I actually printed both of these just to see how they would mesh, and I ended up needing to scale down the inner the flex spline, the inner ring. I had to scale that down a little bit more than I had it for the outer ring, and actually I think I overdid it a little bit. I scaled it from whatever, that 77.3 down another 97%. The nice thing about the flex spline is it doesn't have to be perfect at all, and you can push it. It's flexible. You can push it to engage the teeth. So I'm able to work with that particular print. So I was able to print these out, and then I was able to kind of force these two sides together and then measure the distance in here. And I made a prototype that just used some ball bearings to kind of force the, to create the wave and to push the outer part of the ellipse. I guess I'm struggling because I'm not sure the exact term to call some of these things. But anyway, I had two bearings mounted that push the teeth engagement into place, and then I was able to measure it. So using this model wasn't my first attempt. I actually printed out a really basic model that only used friction, and so you don't actually need these teeth in a flex in a strain wave drive. You can actually use friction. And so as long as you have an outer race of a given dimension and an inner race that's forced into an elliptical shape, the circumference is smaller. If you push that into contact at two sides and that actually rolls along the surfaces on both sides as it rotates, that actually creates the same differential movement without any gears. And so I made one of these, and I actually printed out a elliptical bearing race. The way that I did this was, this is the outer race, and I formed this as a regular old circle, and then this is the inner race that I formed as an ellipse, and then I just created a profile for the bearing and used the sweep function to create the inner and the outer races. I was able to print this out, really no major problems. I just cut a little wedge in here so I could load the bearings in, and I was able to load the bearings. They fit really good. But your printer isn't going to print a mirror-like surface like this. Your printer is going to print, all kinds of issues. And every layer the printer goes around to print, there's a start and a stop point. And those start and stop points, they create little bumps and wiggles and all kinds of problems. And so while I was able to have the round outer race deform itself to fit into the elliptical inner race, there's just a ton of friction. And in fact, there was so much friction that I tried to run it really hard to break it in and to actually have the bearings wear down some of the high spots. But it got so hot that the top part, or the maximum diameter part of the ellipse on this here and down at the bottom, they actually reached the class transition temperature at PET G, which is what I printed these in, and it deformed, and it deformed in such a way that it wouldn't actually create the pressure I needed, because this dimension, which is the most important dimension, actually got smaller as these races kind of flared out at the top where there was the most pressure and the most heat. I lost the entire dimension across here, so that didn't work very well. And because this is an ellipse, smoothing it, is kind of, you can do it by hand, I guess. It would take you quite a lot of time. It would be really hard to do this on a lathe or any other kind of machine. You couldn't like chuck it up in your drill and get a very good result, because while you can spin it, this you're going to be bouncing back and forth with your tool, and if you try to put a tool in here, it's not going to be cutting evenly. So anyway, back over to here. What I decided to do after that experience and testing out this strain wave gear with teeth, I decided that what I could do is print all of the inner and the outer race as regular old circles, and then I could chuck them up, spin them, clean up the race surfaces, and then inside of the inner race, I could press in an ellipse, and that pressing in that ellipse would actually push the inner and the outer races into the elliptical form that I want. So anyway, so back to this. So how did I figure out what the right sizes were for all this stuff? So here I have my nominal diameter based on, I physically printed one of these and measured it. So my nominal diameter for my major diameter for my ellipse. Then I figured out my minor diameter for the ellipse, and then I used the measure tool to get the length. Then based on that length, I multiplied this by pi, and that gave me a diameter. And you can see the diameters right here. It's 52.76 millimeters for the major diameter for the outer race. And then I just worked backwards from there. So I defined a bunch of lines here. I have the plane backwards. So in here, I just basically worked off the outer edge, gave myself a millimeter of material to have in the race. So the ball contact is going to be right here. The diameter of the ball is basically between this point and this point. So it's a 6 millimeter ball. And then I just did the same basic dimension. So it's from the outside of the race to the center of the ball is 4 millimeters. So there's 4 millimeters here and 4 millimeters here. So that's the design parameters I use to create all these different circles. And then once I created those circles, I was able to double check my work somewhat um, uh, by creating another ellipse where this inside ellipse is 16 millimeters diameter smaller. So that's 8. So 4 plus 4 is 8, and then there's 8 on both sides. So 16. So I essentially took 51 minus 16, that gives me 35. And then in this longer axis, I did the same thing, that gives me 38.5. And then if I look at the length of this line, I've got 115.519 millimeters. And if I look at the length of this line, I've got 115.48 millimeters. So there's a very small difference, but it's pretty close. It's 0.3 millimeters ish, 0.4 millimeters ish, and so I went with it. Now I could have tweaked some of these dimensions to make it perfect, but anyway, so I extruded out 3 parts. This inner race, I've got an inner race, an outer race. I just used I think I used the sweep tool, this thing here. I used the sweep tool to sweep a round profile. I think I made the profile 6.2 millimeters to give myself a little wiggle room, and just swept that around to form the races on both the inner and the outer. And then this middle part, this is my elliptical forming jamming thing. I don't know what to call this, but this is what I squeeze into the middle here to force everything else into the right shape. And so I could just drive this with my screw gun. I just made a little hexagonal driving hole, so that I could just put a regular, a standard 1/4 inch driver bit in there, and that's pretty much it. So once I printed the inner and the outer race out, I have a lathe, so I took them over to the lathe, and I used a little carbide burr, a ball-shaped carbide burr, to clean out the inner and the outer races. And then I cut a little loading notch in one side of the race here. I loaded them all up, and then I took this part that I had printed, and I took it over to the arbor press, and I pressed it in. Now, I guess this is the one downside of this design here. If you look at the back of the section analysis, and you imagine putting a whole bunch of load through this inner race, there's not a whole lot of meat here. And I had the bearings in there loaded. The races were smooth. It was spinning really, really nice and smooth. I took this other part and wedged it in there, and actually, it mangled that crap out of this thing. There was one portion of it at the top of one side of the ellipse that I didn't think was savable at all. It was a terrible disaster of a mess. But I didn't have anything to lose, so I made some adjustments, and I just forced it in there, and then pushed the kind of pushed the plastic back somewhat on both sides. And yeah, it actually ran well enough that I could do this squeeze test, which this other bearing design over here, where I printed the inner race as an ellipse, I wasn't able to do that, get that motion. There was so much friction. If you were to squeeze it, there wouldn't be any rotation of the inner race from the outer race. So despite me mangling this when I pressed it together, it actually worked, and I think that's a testament to it's a testament to how much better these bearings will run if you're able to get the right tool in to smooth out the races. And it's also a testament to the fact that, this pressing this into the form actually pushed all of these pieces that got deformed back into the right shape, so that it could operate. So, I think there's a couple other things that you can do with this. This this design works pretty good. The only thing that it's missing, I think, is some ability to add some additional preload. Right now, you have to get all these parts sized exactly the way that you would want them to be sized. So what you'd want to do is you'd actually have this in two halves, and that would make it that wouldn't really make it that much harder to make. So you'd make this in two halves, and then you'd have like an elliptical cam on both sides, and the long axis of the ellipse is running this way, and you put a little driver hole in here, and as you rotate this long axis is going to push these two pieces apart, and so that will increase your ellipse, this major diameter here, and that would allow you to kind of adjust and tension the inner ellipse, and that inner ellipse is what really defines how much pressure you're putting on your flex spline. So there's probably a bunch of ways that you could use to put some additional tuning and something that'll let you adjust this dimension, and or put additional preload. The more preload you create, the more friction you create. But there's a small window of a sweet spot that actually takes all the backlash out of the system, and that's highly desirable for a strain wave. So, I think something like this would work, but in my testing, I just went ahead and used this other design, which again in practice worked pretty darn good. So in summary, the main benefits of doing all this is you get more contact area with less friction and less deforming, which is going to create potentially less vibration by using an elliptical bearing. They're just really hard to make, and using this central deforming method and printing them out round, it actually works pretty good. So that's it. I'm going to plot ahead with playing with this little mechanism. It's pretty cool. I want to try to get something mounted and see what the actual torque that you can get from this output is. I'm very interested to find the practical point at which either the teeth fail, it generates too much heat and fails, or how much backlash is in the system, because I'd like to use it for kind of high accuracy positioning. So anyway, hopefully you enjoyed all that rambling, and thanks for watching.